start by introducing myself. My name is Alp Bassa. I'm head of cryptography at Veridise. So Veridise is a blockchain security company. We do audits, focusing mainly on the ZK space. And today I want to talk a bit about, you heard about Fry most likely, or fast Fourier transform. And so I want to talk a bit about those new fast Fourier transform-like algorithms that have been popping up lately. So you might have been wondering what is the difference between them, how do they relate to each other. So I'll try to kind of convey to you my understanding of how this whole structure works and how they are all related to each other. And since we are in a more colloquial setup here, if you at any time have questions, please don't hesitate to just interrupt and ask your questions. Okay, so the motivation is there are many variations of the fast Fourier transform that are around. Most notably, you might have heard ECFFT, you might have heard recently Circle FFT, especially after Vitalik's blog posts about it. You might have heard about Gala FFT, and you might be wondering what is the difference between all of those. So the aim today is to talk a bit about how they're related, what the differences are, what are the advantages of one over the other, and questions like that. And so this is called the tech room, so it will be a bit more technical, the talk, but if I get too technical, also feel free to slow me down or questions you might have. Okay, so let's start with the fast Fourier transform itself. That's a very classical algorithm going back more than 200 years. And the basic idea depends on this idea of initially how do you represent polynomials. It's something about polynomial arithmetic. So how do you represent your polynomials in your system? The most standard way, the most intuitive way would be to, given a polynomial, let's say of degree n, over a given field. In our case, the field will be a finite field. Given such a polynomial, you represent it by just listing all the coefficients of the polynomial as a vector, right? So this is also called the time domain or the coefficient form. The name time domain sounds a bit weird, but there are reasons for it. But what you could also do is you could use the fact that a given polynomial of degree n is uniquely determined by its value at n plus 1 different points. If you know the evaluation of the polynomial at n plus 1 different points, you uniquely can pin down what the polynomial is. And the idea is then, okay, let me just store the value of the polynomial at n plus 1 predetermined points that I have. So this is called the evaluation form, obviously, because you're evaluating at those points. And then now we have two different representations. And going back from one to the other is something which in linear algebra, if you remember it from college years, is just something you would have called a change of basis. Yeah? So it will be just corresponding to just multiplication by a change of basis.
Do you really have like a sort of real world example to tie this?
Yeah, sure.
Yeah, so really like,
yeah, sure. So let's just take any polynomial. Let me just take the polynomial 2x squared plus x minus 5, right, over the given field, whatever. So the coefficient form will just store the coefficient. So the leading coefficient is 2, then I have 1 in front of x, that's not visible, but then minus 5, right? So that would be what I call the coefficient form there. If you want the evaluation form, you have to fix evaluation points. Those are predetermined. You could just take 0, 1, and minus 1. We don't want to evaluate like big things, at least not on the whiteboard. So you would just substitute those values into the polynomial. So for 0, so if this is your polynomial f of x, you would have f of 0 is equal to 2 times 0 squared plus 0 minus 5, which would give you minus 5. If you do the same, if you look at the value of 1, you would get 2 times 1 squared plus 1 minus 5. So that would be 2 plus 1 is 3 minus 5 is minus 2. And then finally, the value of minus 1 would be 2 times minus 1 squared minus 1 minus 5, which would be just minus 4, right? And then you would be just storing the three values, minus 5, minus 2, and minus 4. Yeah. And this would be the two ways of representing the very same polynomial, but in different forms, basically. And once you know what those fixed evaluation points are, you can go back and forth between the two values. Yeah? So, I mean, going from here to here is just evaluation. Going back from here back to here would be, I'm giving the value of the polynomial at certain points. I'm asking what is the polynomial that evaluates to these values at these points, and that's just solving linear equations, basically. But that's what we would call interpolation. Yeah? Okay, so it's basically writing the space of polynomials in two different bases, right? And why is this useful? I mean, the way you represent something dictates a lot what you can do with it, right? And in this case, if you represent it in an evaluation form, it helps you a lot, for instance, with polynomial evaluations or multiplication operations, right? So if you want to multiply two given polynomials, right? We have, let's say, two polynomials of degree n. If you would just multiply them in the usual way, you would just take all possible cross terms, add them up, and so on. So you would do, the number of operations you would do is at the order of n squared. You can do it a bit smarter. You can do it with like Karatsuba kind of methods. You can take it down to order of n to the 1.59. But then this is for the way when you represent them in terms of their coefficients, right? But if you represent your polynomials in terms of their evaluation, right, then you can just use the following fact. I mean, I know the evaluation of both polynomials, f1 and f2, those are the polynomials I want to multiply. I know their evaluations at various points, and what I want to do is I want to find the evaluation of the product of those polynomials at the very same points, right? But then the value of the product of two polynomials at a given point is just the product of the values of the polynomials at the same points, right? It's a mouthful, but it's nothing too complicated. So basically it means once you represent your polynomials in evaluation form, if you want to multiply them, if I have given two evaluation forms of two different polynomials, if I ask, okay, I take the product, what is the evaluation form of the product? All you have to do basically is just to do component-wise multiplication. You take the values at each of the evaluation points of both polynomials, multiply them together, and that will give you the value of the product of the polynomials at the same evaluation point. Yeah? And this time, you see, this way you get a very fast, it will be an algorithm that's linear in the degree. That's something you cannot do if you don't know how to do it in the case where those polynomials are represented in coefficient form. Yeah? But then you need to go back and forth between the evaluation form and the coefficient form. So you will need to be able to evaluate polynomials very fast, right? Because I mean, in the end you want to go back to your polynomials and so on. And for that, you will need what is called like fast multi-point evaluations. Given a polynomial, you want to be able to evaluate it in a very fast way in many different points. And that's exactly where the fast Fourier transform comes into play, right? So how do you do that? I mean, basically what you do is you choose for the discrete Fourier transform over a finite field, you're working over a finite field. As your evaluation domain, you will choose a very particular set, namely you just choose the nth roots of unity. Yeah? So those are those elements in the finite field such that when you raise them to the power n, you just get 1. Yeah? So the second root of unities would be 1 and minus 1. If you look at the fourth root of unity, like in the complex case, they would be 1, minus 1, I, and minus I. Yeah? Okay. But then, if you want those roots of unity to exist, you get a condition that this n should divide q minus 1. This is a basic fact from algebra. If you want the nth roots of unity to be defined over the finite field you're working with, you need that this condition is satisfied. And this puts some serious restrictions on which finite fields you can work with. Okay, so now we have this evaluation domain, and what we do is just, given a polynomial f, we evaluate it at those roots of unities. Yeah? That's nothing special, just what I had talked about before, but your special points of evaluations are just the nth roots of unity. Why is this useful? I mean, there is this very particular case of the discrete Fourier transform, which is the fast Fourier transform, which corresponds to the following case, where you choose your n, that was the order of the roots of unity, you choose that to be a high power of 2. So n is 2 to the power k. You evaluate your polynomials at n different points. And now the condition that n divides q minus 1 turns into a condition that 2 to the k divides q minus 1. And given that condition, if it's satisfied, you have those roots of unities. And why is that useful? It's useful because given a polynomial f of x, what you can do is you can always split it up into an even part and an odd part. Yeah? So let's go back to this polynomial that we had over here. You can just take those terms in the polynomial that appear with an even exponent. So here you have exponent 2, here you have exponent 0. So those are the two even components. And then you have one odd component in this case, which would be just this one term that's the x, right? So given a polynomial, you can always separate it into the even part and the odd part, right? So this f0 and f1, those will be polynomials defined by f, and this will just give you the even terms. This will give you, again, even terms with the x here, it will give you odd terms. Right? And then the nice thing is, because of this x squared term that you have inside here, the degree of each of these polynomials, f0 and f1, will be at most half the degree of f. Yeah? So we wanted to evaluate our polynomial at points. If the degree of the polynomial is higher, you have to do more work. What we have done is we have reduced the problem of evaluating a given polynomial of a given degree to the problem of evaluating two polynomials of half the degree. So nothing is gained yet, because rather than evaluating one polynomial of degree n, I evaluate two polynomials of degree n over 2. But you can use the following fact. So the roots of unity were of a very particular form. They were 2 to the kth root of unities. Right? And there's this very nice fact that if you take 2 to the kth root of unity, or let's say nth root of unity where n is 2 to the k, if you square it, you get n over half root of unity. Yeah? So you should think of this as you have a set of roots of unities that you have chosen as your evaluation domain. Right? So the nth root of unities form a certain set, S0. So those are the nth roots of unity. And then you do a squaring operation, and then you're mapping all of it to n over 2 root of unities. So I'll denote this set by S1. And you see the evaluation domain, once you square, is shrinking. Because here you will have a total of n elements. Here you will have only n over 2 elements. So that's the nice thing. Not only do the degrees of the polynomial get half, but you also have the advantage that the number of evaluation points also is half. Because those x squared terms, they will fall into the smaller set S1. And you can not stop here, but continue recursively. Once you have f0 and f1 that you need to evaluate on the set S1, you can write each of them again in terms of odd and even parts and just continue recursively. Yeah? And if you do that, you get basically what is the fast Fourier transform. And so it sounds scary maybe if you have not heard of it, but the main idea is just very beautiful and very simple. Yeah? It's been used already by Gauss in the beginning of the 19th century. Yeah? Okay, good. So, but then, as I said, we had this condition that q minus 1 is divisible by a high power of 2. Yeah? This divisibility, you need basically to have this fact that these sets S0, S1, S2, and so on, they always get to half the size. Yeah? To have this phenomenon that your evaluation domain shrinks, you need that q minus 1 is divisible many, many times by 2. And this puts really some restrictions on the field over which you can work. So people started looking for fields such that the size of the field minus 1 is highly divisible by 2. So Plonky 2 uses what's known as the Goldilocks prime. If you look at p minus 1, you get this term over here, which is divisible by 2 to the 32. Or risk 0 uses baby bear, where the power of 2 dividing p minus 1 is 27. But this kind of restricts where you can work. You might not want to work with these very particular primes. You might want to work with primes that offer you a better arithmetic. So you might wonder, can I get around this restriction on the prime? And there are many variations that you can do. There's, for instance, you could just look at third roots of unity rather than second and 2 to the nth power roots of unity. You would just divide it into not odd and even parts, but you would have the parity modulo 3. You could do other tricks like the discrete Galois transform, where you basically now assume that p plus 1, not p minus 1, but you assume that p plus 1 is divisible by a high power of 2. And this allows you to work over primes like the Mersenne primes. Like 2 to the 31 minus 1 is known to be a prime, right? And you can work over that field. And because of the very particular structure of the prime, many operations will be very fast on the CPU. Yeah? But then, so what's the idea behind? I will not go further into detail because it's quite technical, but basically, there is a variation that works for primes p such that p plus 1 is divisible by a high power of 2. And this might remind you of what's known as the circle star, so I'll get back to that later on. And then you might wonder, what are other options, right? Well, I mean, what's so special about these two examples that I talked about? And if you have heard about ECFFT or circle stars, what makes them so special? Can we find kind of a unifying view on all of them and have a better understanding? That's what you want to do, and for that you just need to have a better understanding of what's really happening kind of behind the scenes. So basically, you see the main thing that happens, that changes something, is the squaring map over here, right? That's the one that takes your polynomial, separates them into odds and even parts, and that's the part that takes your evaluation domain, shrinks it to a smaller evaluation domain. So there's something particular about this map x squared. Once you understand that, you can hope to generalize things, right? So this is just how the graph of the x squared map looks like, right? This is the complex picture, right? Over each point over here in the plane and the complex plane, you have 2 points mapping down to it, except the origin will have only a single point mapping to it. And here you should think of this is the curve y is equal to x squared, right? So you're mapping onto the y-axis, and for each y value you will have 2 points that map to the given. Yeah, so that's kind of how you should visualize the map x squared. And it has this very nice property that generically, almost at any point, it is a 2-to-1 map. Yeah, so there are 2 points that map to one given point over here. Yeah, or if you want, you could just take this coordinate axis onto which you're projecting. You can pull it down, so you see better that for any 2 points, there will be, pairs of points will be mapping to the same point, except the one exception, which would be the point 0, which would be mapping to a single point. Yeah. And then what you can do is you can say, okay, I want to take this, I will call this, in algebraic geometry, that's what they call a covering of curves. I have a more complicated curve up there that would be corresponding to the parabola. It's mapping down to a simpler curve. This is what is known as a covering. For a given point, I will have a certain number of inverse images up there. And just like at the point 0, there might be points with multiplicity. Yeah? But let me not go further into details here, but basically you can say what I have in the squaring map that forms the basis of the FFT is a covering of curves. And what property does this covering satisfy? It had this property that on the top level, this is just an iterated way of looking at the same map. You look at various copies of the squaring map. And it had the nice property that at the very top, you have a certain set, which is mapped under the squaring map to smaller and smaller sets. Yeah? So you basically, if you have a given point in the set, you also have the other point, which forms a pair with it, so that once you look at the image, you get a smaller set. Yeah? And rather than starting with S0 and going all the way down and then hoping that the S0 will work, you can just start with a point down here and then go back up, taking at each step both of the pairs that are in the inverse image. You can build up your set S0, which will then have the property that with the given map it behaves in a very nice way. Okay, and then what's more involved, another thing that's involved here is we had this very particular property of the nth roots of unity. We were working with the nth roots of unity, and they have this nice property that they form a group. Yeah, so you can take two nth roots of unity, multiply them, you get another nth root of unity always. And this has the structure of what we call a cyclic group. Yeah, and this will be important later on. So basically, the set of points that you look at, your set S0, will be one orbit under this action of the groups, so to say. Yeah, so there's some group involved, there's some symmetry involved that makes things work very nicely. Yeah, I will not go too much into details here, but basically, once you translate everything into the language of curves, you see very nicely that, I mean, I'll just skim very quickly over this. You can reinterpret everything in terms of curves, coverings of curves, maps between them, and like some arithmetic of those curves involved. But then you might wonder, okay, there was this group involved, right? I mean, the nth roots of unity, they form a very nice group. If I don't want to work with the nth roots of unity, what other options do I have? Yeah, so basically, you are kind of forced to look at automorphisms of the line. Yeah? And so those would be, I mean, on the line, the automorphisms would be given by 2x2 invertible matrices, right? And in the case that we saw before, the matrices would just correspond to multiplication by roots of unities, right? And then you say, if I want to generalize this, what do I need to do? I need to find other automorphisms groups of the projective line. And then you can go back, not too far in history, not 200 years, only 100 years this time, and you'll find that people already have thought about this problem. They have classified all automorphisms, all finite automorphisms of the line, and this is solved by Dixon. It's known as Dixon's theorem. It tells you basically what the groups are that you could encounter, that you could hope working with, right? And I mean, you have the elementary abelian P groups. It's not too important what those are if you're not familiar with group theory, but you should just think of these as certain symmetries of the line that you can have. Yeah? It classifies all possible symmetries. You can have what's called elementary abelian P groups. You have cyclic groups, and the cyclic groups have order P to the m minus 1 and P to the m plus 1. Yeah? And P to the m minus 1, that should remind you of the FFT. P to the n plus 1 should remind you of this generalization that I had talked about afterwards. And you have dihedral groups that come in a big family, and the rest are just some sporadic ones which are not too interesting things. Yeah. And then what you can do is you can go back and say, can I engineer some new variation of FFT using those? Yeah. And basically, you see that what I have talked about, the two examples before, corresponded to those two cyclic groups. If you look at the circle FFT, it will correspond to the dihedral group. And then another way of generalizing things, there is also the elementary abelian P groups, which would correspond to what's known as the additive FFT. But then the next thing you could think about, I'll just skip very quickly over these. But you can say, why do I work with the projective? Why do I work with the line? Can I not work with more complicated curves? And you can do that as well. You can work with elliptic curves, and they already have a very nice group structure on their own. And you can exploit that structure and isogenies between those elliptic curves. And if you do that, you get back what is known as the ECFFT. I'll not go into details of those. Let me just say that this way of looking at things will give you a very nice unified view of all the different variations that are around there. And it also gives you the possibility to make statements like, okay, this is what is known, what has been discovered, and there's only this, and that you could do additionally, and there's nothing else because of a result by Dixon from more than 100 years. So, and there are many open questions you can ask about this further, but I'll not dive into details there. So just thank you for your attention. there are any questions, I'll be happy to answer.